I guess that means we should start. All right, welcome back, everyone. Still Jeff Renica, still at Colorado School of Mines. So I guess we will go ahead and jump in. Looks like there's been one question in the chat already that I'll bring up to speed for those that join later or watching the recording later. Kelly just wanted to know why material scientists don't care about space groups. So I made that comment in the last class, and it's as most of the things that I'll probably say in here, a bit of an overstatement. There are a lot of material scientists that do care about space groups um, because the each space group there's a direct correlation between space group and point group, and the point group symmetry is what determines the properties. So for a given point group, that might encapsulate one or five or three or some other number of space groups depending upon the translational symmetry that can be added to the point symmetry of the point group. And therefore, the point group symmetry also dictates the properties of all of the space group symmetries that are within it. And so by saying that space groups don't affect properties, they don't affect them uniquely beyond the point group. And so hopefully that helps to clarify a little bit. There are a lot of material scientists that really do care about space groups. Just when it comes to the kinds of properties that we're talking about here. So symmetry derived properties, piezoelectricity, ferroelectricity, those kinds of things. The anisotropy of elastic modulus, all of these kinds of things that depend upon the unit cell and the properties of that symmetry. The space group is what determines it, and then that trickles down to the individual space groups. The point group determines the properties, the symmetry of the properties, and then that trickles down. Hopefully that clarifies. Yeah, let's jump in. We are a little bit ahead of schedule, so that's great. That means that we have more time to cover other things. That also means that if you want me to slow down, if you want me to stop and ask questions along the way, please do. Seeing a lot of words in the chat coming up, so I'll do my best to address those as we go. Thank you to those people that submitted a little bit of information on your background. That'll help me tweak the way that I'm presenting things and the exact content that we use later in the class, especially once we get into a little bit more details in particular material systems and application examples and that sort of thing. So if you have any of those that you want to pass along, please do. All right, we'll jump in. So today gets to be another, at least the first portion of today gets to be a lot more background on things that you may not consider electrical ceramics, but they're essential to be able to understand what we're going to get to later. So how do capacitors work? Why do we need to engineer the material in this way to get this kind of performance? When we get back to more details on ferroelectrics and piezoelectrics and those kinds of things. That's why we're going to be covering some just basics of circuits so that we can understand how to engineer the materials as we go. So we're going to stick with basic RLC circuits, resistor, inductor, capacitor. And in fact, we're going to not spend a whole lot of time on inductors. So it's mostly just resistors and capacitors. We talked last time about conductivity. And so we're just applying a field. We get conduction. Hopefully you're all familiar with Ohm's law, V equals IR. From that, you can calculate the power. So the power is just the P here, I squared R. If you've heard of I squared R heating, if you've perhaps bought a furnace element from I squared R, that's what this is referring to. It's how much energy is actually dissipated by that electric power. Then we can start putting different components together. And so the way that the fields and the currents are distributed as you have multiple different simple components, simple circuit components. This is the reason that we're going to talk about circuits at all, because as we start engineering microstructures, we can represent individual components of the microstructure as different pieces, or maybe beyond microstructure, all the way up to individual components. We need a capacitor of this kind of characteristics over here, and we need a different resistor of these kind of characteristics over there. We need to understand how the electric field and associated current will be distributed among those. So to start off simple, you throw a couple of resistors together. The sum of that resistance is just the sum of those two resistors. That is fairly intuitive, I think, but then when you put them in parallel, you just have to remember that electricity, like water, is going to take the easiest path. So if you've got a couple of resistors in parallel, the lowest resistance is the one that's going to get the most energy. And so you're going to have the most current flowing through the lower resistor. And so the way that works out from a math perspective is that the inverse of the total resistance is the sum of the 1 over each of the components. Again, please stop me if you have questions about any of these. When we do this for capacitors, this is the part that starts to get confusing for some people, and it confused me a lot when I was first introduced to it. I just had to suck it up and deal with the equations, and then it became a bit more intuitive as I worked with things a bit more. If you have a pair of capacitors in series, so the way that we represent that is we've got a capacitor and another. We throw them together in series. A very simple way of looking at that, you could just sort of X out this center part and you have just 2 electrodes. And so if you look at it that way, if you remember what goes into capacitance, there's the area and the thickness dependence. It's sort of like just increasing the thickness of your capacitor. And so it makes sense that the overall capacitance is going to go down. So what happens from a mixing rule perspective when we've got additional capacitors in series, you end up dropping a little bit of voltage across each one of these. And so the overall energy that you're able to store in that capacitor actually goes down when you have capacitors in series versus just having one. Or if you have multiple capacitors in parallel, then that's very similar. It's analogous to just increasing the effective area of one of them. So you can look at 2 capacitors in parallel as just being, oh, I've got one capacitor now. It's just got two different components that increase the area of the whole thing. So I stick them in parallel. Now I can store more energy in those. And you can see that represented in the equations. So again, no need to memorize these or anything like that, but just get a grasp for when you see mixing of different components and then try to translate that to what we see in the microstructures of the materials that we're going to be building and those kinds of things. So eventually we're going to be able to look at a whole series of grains where you've got grains and you've got grain boundaries, and we put those all together as a mixture of resistors and capacitors and understand how this is all going to happen as one composite piece. If each one of those, for example, the grain might be conductive and the grain boundary is going to be insulating. And so it looks like a capacitor in series with a resistor. And then you get to the other grain boundary and there's another capacitor that's in series. And now you spread it across the actual physical width of the material. So we have to deal with the fact that they're in parallel now. These are the basics that go into that composite mixing rules. How do we know if the grain boundary is insulating? That is an excellent question. We're going to get later on in today's lecture to impedance analysis. And the unsatisfying answer is that what we often do is come up with a model that is a guess. And then we go in the lab and we make a measurement and we say, if this model that I created in my head and wrote down on paper is actually representing what our real sample is in the lab, this is what the impedance spectrum would look like. And, oh, it doesn't match. Well, I need to go back and make a different model and see what that would look like. And so it's a very iterative process. And we can sort of educate those guesses by saying, I know my grain size is about this. I know my the defect chemistry should be such and such. And maybe it makes sense for the grain boundaries to be conductive in this case. And then I would see this kind of response. So it's a lot of guessing and checking. Experimentally, you can, for example, go in with a scanning probe microscope, an AFM or a PFM or conductive AFM, and actually measure locally and see the distribution of conductivity, of permittivity of different things. There are other clever ways of doing this. You could put down microelectrodes and measure across a single grain boundary and those kinds of things. All of the tools that are available for that, though, depend upon you asking the right question about what is it I'm really trying to learn here. And so a lot of that usually comes from, I made a sample, I measured it the easiest way possible, and I came up with a hypothesis, and then I'm going to zoom in and test that. So we'll get, as we go through this, we'll get to a few examples where examples of where it's useful or problematic or common or all of the above to have very different resistivities, capacitances, those kinds of things at grain boundaries versus grains, and hopefully hopefully be able to tease out, use these kind of techniques to tease out what's going on in the real material. All right, so a capacitor. I mentioned this on the last slide. I probably should have thrown this one up first, but the overall capacitance of any capacitor is you're really just storing charge, which is Q, and that's the amount of charge that you can store in a capacitor. So a capacitor is really just an insulator of some sort. So you're not allowing current to flow. So you can imagine if this was a continuous wire, then you'd have current flowing there. And instead of having that continuous wire, we've blocked the passage of electrons in some way. So we've put an insulator in there. In this case, we're going to start with that insulator just being vacuum, just empty space. So the capacitance depends upon the area. So how big are those plates that you're able to store the charge across, and then how close are they together? So the closer the plates are together, the more energy you can store, the more charge you can store. The larger the area, the more charge you can store. So you can see from this equation over here that you've got these two permittivity factors, and then you've got just area and thickness. And so large area means large capacitance, small thickness means large capacitance, and then we've got to deal with these two. So the epsilon R and epsilon naught. Epsilon naught is here's the quick animation of current flowing in. We flow current and eventually build up charge because the current can't go anywhere. And so that electric field that's between there, that ends up being the voltage. So voltage is just the field times the thickness. So if we're not allowing current to flow, then that's where these charges are going to build up. The epsilon naught, epsilon zero, is the permittivity of free space. So that's a fundamental constant that says if you've just got vacuum between these plates, that's the amount of charge that you're going to be able to store on the capacitor. But real materials are going to have a relative permittivity, this epsilon R, that's larger than an epsilon naught. And so when we and we can discharge this capacitor, the current's going to flow away. And so from that, you can probably see if we go back, we're going to add charge, and then it's going to flow away. So we're going to actually have a time lag between the current that's flowing in and the current that's flowing out. So if we go back to Ohm's law, if everything is just a perfect resistor, we apply voltage, current flows, there's no shift in time. But now we've suddenly shoved this gap in there. And now as we apply a field, the current's flowing and it gets stuck, and it sort of piles up along these capacitor plates. And then you turn off the charge and it flows back the other way because it's all built up, and that capacitor is going to discharge. And that gives us a time lag in between the amount of voltage that we're applying, the amount of current that we're getting, and then the voltage that's actually on the capacitor. So that's represented if we have a sine wave, like you would have coming out of the wall when you plug something in, then the capacitor voltage is going to be offset by 90 degrees in time from the applied voltage. So this will be really important when we start looking at AC circuits in a little bit. All right, so that part applies no matter what flavor of capacitor you have. So it's anytime that you're going to have an insulator that's blocking charge. That is really all a capacitor is. If we want to actually do something useful with this, we probably want something more effective than just vacuum. So we can throw a solid material in there. It doesn't have to be solid, but we'll stick with ceramics. And we're gonna stick some sort of a material in between these plates, and that will allow us to store a higher charge density because those charges flow into the plates and they build up, and because you have anything in there, it will actually respond to that field and stretch the bonds of the insulator that's in there. That allows you to store more charge. That's what increases the capacitance because it increases that relative permittivity, that ER. The time lag associated with that, though, is what we represent in this top plot. So in this case, we're looking at the Z is just impedance. So you can think of it as the resistance for an AC circuit. And then we've got the real and imaginary components here. So the real part is the actual stored energy, the capacitive portion, the imaginary part. And this is confusing use of imaginary. It is actually real. It's a valid thing. But from a math perspective, we use imaginary because we use the square root of -1, like you do in physics and EE and all these kind of fun things, to represent that. So it's just saying that's the out of phase component. So we can draw one of these, what's called a phasor diagram. And just if you look at the angles between the real and the imaginary components, we're not going to have to draw these diagrams. The point is that you will often run into a parameter known as tangent delta. So tan delta is really just the ratio of the imaginary over the real. And so that means if you have a large tangent delta, that means that you have a larger imaginary component compared to the real component. And so this delta angle is really just telling you the relative amount of energy that is lost versus the amount of energy that is stored. And when you look at that on a on the time-dependent response, that's telling you how much things are shifting. So if it's sitting right at -90 degrees, that would be an absolutely perfect capacitor. Tangent delta would be 0. In a real material, it's never 0. It's always shifted just a little bit. And so we represent that as this tangent of the delta angle that tells us how far out of phase things really are. Hopefully that didn't stumble through that too much. There's going to be a lot of equations up here that are really just meant as reference in case you need to go back and look them up later. I'm not going to bore you with walking through every single equation, but I do think there are a few pieces in here that are going to be important because they come up over and over again. So when we look at a capacitor, again, the Z is the impedance. So that just tells you what's happening when you're applying a field to it. The impedance actually varies with 1 over the frequency and the capacitance. So the higher the capacitance, the lower the impedance. The higher the frequency, the lower the impedance. And then we've got this J or negative J. That's the square root of -1 aspect that we're going to be dealing with. So that tells us relates to the imaginary component of the circuit. When we put a resistor and a capacitor in series, so this would be, for example, if we have an insulating grain boundary and a conductive grain, then you could represent that as the conduction through the grain as a resistor, and then an insulating grain boundary which stores the charge. That would be one example. You could also flip things around, but you'll see this tan delta. That is the measure that we're going to use for how lossy or how much we're dissipating energy in such a circuit. And so when we start with just these very basic examples, we've got one possibility where there's a resistor in series. So in this case, this would be a resistor and a capacitor in series. And in this case, we've got a resistor and a capacitor in parallel. And so the easiest example of the resistor and capacitor in parallel is shown right over here. So that is, I have the brown material is whatever I've shoved in as my dielectric in this capacitor. And if it were 100% perfect and ideal, there would be absolutely no resistance. There would be no leakage through it. But we all know that there's no such thing as the perfect material. There's always going to be some amount of leakage. It's not an infinite resistor. And so the leakage through that material we can represent by this resistor. And so the easiest way to represent that is say, oh, well, if the material were absolutely perfect, here's what the capacitance would be. And then here, this resistor in parallel is how I represent the amount of imperfection. So how much is leaking through that because it's not exactly perfect. So we will, for good insulators, for good capacitors, we will use this parallel model a lot. And you'll notice on here that the tangent delta, so the amount of energy that's dissipated, so that the ratio of lost energy to stored energy is inversely related to the size of the capacitor, the size of the resistor, and the frequency. So basically that means that when this model is most appropriate, then you will see the tangent delta decrease as you increase frequency. So as you go faster, you don't have as much time for that leakage current to contribute to end up dominating. So if you're wiggling your electric field back and forth fast enough, then the charges don't have time to leak all the way across and then leak all the way back. Any questions on that? All right, we'll continue on with a little bit more detail about these kinds of circuits. So if we're at low frequency, then it probably makes sense that we're going to be dominated by that parallel resistance. Because at very low frequencies, we've got a lot of time for charges to leak through that resistor, that imperfect material. As we increase the amount of the frequency, that's going to matter less and less and less because of this 1 over omega RC. And eventually we're going to get to some sort of plateau region where we're no longer dominated by the frequency dependence of that. Maybe there's something else that's dominating in that region. There's going to be some practical minimum to the way that we're measuring it. We may never actually see that flatten out. You might actually just go all the way to the point where you turn around and suddenly if we get the high enough frequencies, we're going to be dominated by this series resistance. So that just means that now we're in a region where the tangent delta is increasing as we increase frequency. So what does that mean? It means that the leakage through the capacitor is no longer the thing that's dominating our loss. Now it's this resistor that's in series. So what does that mean? I thought we had a capacitor that we were describing as being this imperfect thing that had some leakage through it. Well, at low frequencies, yes, that's what dominates. But as we get higher and higher in frequency, there's these metals are also imperfect. So there's some resistance associated with getting the charge to the capacitor in the first place. And once we get to high enough frequencies, then the series resistor, so the amount of resistance getting the charges to and from that storage plate, can actually end up dominating. And maybe, in fact, it's the resistance of the plate itself. So if you have a very thin resistor or very thin electrode there, that can be a relatively large series resistance. So these are simple examples of the kinds of behavior that you'll see in real materials as we start measuring them. And so because of this, just doing a simple measurement of tan delta or of capacitance as a function of frequency can tell you a lot about what's actually happening inside of your capacitor, inside of your material, inside of whatever your insulator is. So if you can actually see this transition point, then you'll know when you're dominated by the leakage within the material versus dominated by the circuit getting the charges to the insulator itself. So you'll notice I don't have any numbers on here. So what frequencies does this transition actually happen? It depends. It depends on everything. So it depends on the size of the capacitor. You'll notice both of these have R and C in the equation as well. So the larger the capacitor, the sooner you're going to get this transition, because the tan delta in series is going to depend upon both the resistance and the capacitance in series. So for large capacitors, that sort of transition period will happen at lower and lower frequencies. So one way to think about that is, for a large capacitor, you have a lot of electrons that you have to get there and get out and get in and get out. So that's a lot of current. So moving a lot of current takes time. So if you have a very large capacitor, then it takes a lot of time to get a lot of current into and out of it. And the resistance that's in the way is also going to play a direct factor in there. So every aspect of this matters. So the amount of capacitance, the amount of resistance, and the resistance, again, if you remember back to Tuesday, we talked about just resistance being rho L over A. So it's how long is your wire, how fat is the wire to allow charge to flow through it. All of these things end up mattering. And we haven't even dealt with inductors yet. So this is just starting with the basics of resistor and capacitor. So questions on this so far? All right, we are going to end up, I promise we're going to end up using these and for trying to understand what's happening within our samples as we get further along. So when we've got these mixing rules, now we can look at what's actually happening inside of a composite. So we might have an intentional composite of two totally different phases. So maybe we've got a 3-1 composite that we've made for a sonar array, where we have a capacitor and a ceramic piezoelectric and a polymer. Or maybe it's a different scenario where we've got intentionally two different phases of something that are built together. If we just stop with real materials and go back to assuming that everything is perfect, we'll still have a distribution of electric field. So even if these are absolutely perfect insulators, and we don't even have to worry about the resistance that we just talked about, just having multiple different permittivities will change the way that the field is distributed within a material. So in parallel, if we've got two different phases in parallel, then most of the field is going to go into the material with a high permittivity. And so relative permittivity, you may have heard it as dielectric constant. I hate using the phrase dielectric constant because it's anything but constant. As we will keep coming back to later and later in this course, the relative permittivity changes with temperature, with frequency, with composition, with voltage, with everything. And so the fact that people refer to it as a constant is just really confusing because it's not constant. So relative permittivity is a mouthful. I might slip up and call it dielectric constant, so I apologize for that, but just keep in mind that it's not at all constant. So when you've got these materials in parallel, so if you've got a large capacitor next to a small capacitor, that large capacitor is going to take all the field. However, if you put them in series, so maybe you've got a high capacitance material here in blue, and then a low capacitance material in gray that's sitting in the way. So this would be in series. Now, most of the field is actually going to drop across that low permittivity material. And so this basically all comes down to Gauss's law, if you want to go back and rederive all that fun stuff. But applying it really just means that when you have things in parallel, the high permittivity material gets all the field. When you have them in series, then the low permittivity material gets all the field. So if you go back to the structure that we had for that capacitor, if I want to put a large permittivity material in here to store a lot of energy, and I accidentally leave an air gap, most of the field is going to drop across that air gap. And so it's complete waste that I put all this effort into buying an expensive, fancy, high permittivity dielectric to shove in this if I left it air gap, because all the field ends up dropping across that air gap. And so that kind of concept we'll come back to over and over again because it really matters in terms of the way that the performance that we get out of capacitors and alternatively piezoelectrics as well, and ferroelectrics. So we don't always have a perfect lamellar structure like we drew in the first two examples. A lot of times you'll have a blob of something within a matrix, or that blob could be high permittivity, it could be low permittivity. But whenever you have a disordered composite along these lines, again, the same concept of in parallel, the field lines are attracted to the high permittivity, and in series, they're going to be concentrated in low permittivity. Those continue to apply. And so you can end up getting very funny looking distributions of electric field lines within these kinds of composites. One easy way to model them, at least at first order, I wouldn't call it a predictive model by any means, but it's really good at representing sort of back of the napkin first guess calculations. You can just do this Liechtenegger approximation that says that the logarithm of the composite permittivity is basically just the volume of each of the phases times the logarithm of their contributions. And so that means that if you've got a high permittivity here and a low permittivity here, instead of being a linear response, and I apologize for my lack of artistry, instead of getting a linear response, you actually get a bowing. So hopefully that makes sense. If you ever need to guess at what the permittivity is going to be for a mixture, that's a good first step. All right. Another chance for questions on the basics of mixing rules and series and parallel capacitors and resistors. Now we get to dive into what's actually happening inside of the material itself. So this is where we start to get into the real material science. That's the fun part. So we take any insulator that we care about. It doesn't matter what the chemistry is. We apply an electric field to it. If it's an insulator, then that means that we can actually sustain an electric field. If it's a conductor, then the charges flow, and that's not there's no field there. If it's an insulator, there are multiple different ways that the material can respond to this electric field. So at its absolute most basic, polarization is really just separation of positive and negative charges. That's it. Within real materials, there are a number of different types of positive and negative charges. So each one of these ends up representing a polarization mechanism. And so the very most basic of these is going to be just the electrons flying around the nucleus from the positive nucleus. And so that's what we represent here with the electronic contribution to polarization, polarizability. That's just saying the electron cloud is negatively charged, the nucleus is positively charged. By applying an electric field, the electrons are going to want to shift over towards the positive side of that field. The nucleus is going to want to shift over towards the negative side of that field. And that stretching of the atom essentially gives you a very, very tiny dipole where you've got a separation of positive and negative charges. Hopefully that makes perfect sense. So now we've got the electron cloud stretched a little bit. We've got the nucleus pulled the other direction, and now we turn off the field. What happens? It's going to respond back and try to become a sphere again, or as close to a sphere as we're going to assume for a very simple atom. Because you having that separation of positive and negative charges is a higher energy state than everything balancing out. And so every material has electrons. Everything has a nucleus and electrons. So we apply a field, we're going to get this kind of stretching and response. You'll notice on here, on this plot, that there's a resonance associated with that. And what that means is when there's going to be a natural harmonic frequency associated with the stretching. So you can picture it exactly like a spring. In fact, we use simple harmonic oscillator spring models to model what happens in this. You apply a field and you stretch that and you let go, and there's a restoring force that makes the negative charges and positive charges come back to a center, to an equal center. And so because of that restoring force, that means that there's a natural spring-like harmonic frequency. And so as we get close to that frequency, we're going to get positive feedback and get a resonance. And if we're just above that frequency, then things are way out of phase and you just end up dissipating all of your energy and the permittivity drops actually below 1. And you'll notice down here this loss, which can be represented as tan delta or loss, many, many different flavors of that. Then the loss is actually going to maximize right with that as well. So that's sort of the spring-like nature of that restoring force is what causes that to be a resonance. So these are the kinds of this electronic polarizability, this electronic polarization happens in everything. And this is what relates to index of refraction. So it's actually the index of refraction squared is the electronic contribution to the polarizability. So index of refraction squared equals the ER for electronic. So that means that anything that has electrons and has a nucleus is going to have an index of refraction, and it's going to have this electronic contribution to polarizability. That doesn't mean that it may not dominate So if you're familiar with index of refraction values, an index of refraction for any solid that's maybe 2 is really high. So index of refraction is basically the ratio of the speed of light within the material to the speed of light within free space. And so slowing down light by a factor of 2 is a lot. There are a handful of materials that have a really high index of refraction around 2, but most things are in the 1 point something range. So if we're trying to take advantage of this contribution to store a lot of energy, we probably need something stronger than just pulling the electron cloud and the nucleus apart from each other. But the nice part of this is that it's applicable all the way up until the response of that spring just can't keep up with the applied electric field. And so you're probably familiar with the fact that photons, just light waves, are electromagnetic waves. So that's that electromagnetic part of it that's applying the field as you're interacting with the electron cloud. And so the mass of the spring that we're talking about for this resonance is so low because we've got just a handful of electrons and a nucleus. That's why it can respond to very, very high frequencies. And so you end up with Droog type behavior at these really high frequencies. If people are interested in optical properties, we can get into that later in the class. But basically, we're going to focus most of our time at lower frequencies, where we can start to engineer newer, larger contributions to that permittivity response. And so the next largest sort of spring that we can deal with are those ionic bonds that are present in anything that's ionically bonded. Some things that are going to be covalently bonded are going to have some contribution that's equivalent to this. But basically, we're taking a positive cation and a negative anion and stretching them apart. It's the exact same concept as we saw with the individual atoms and the electronic contribution, but now instead of just stretching the electron cloud a little bit around its nucleus, we're actually pulling the cations and the anions apart. And so this is really just lattice vibrations, but it's doing it in a way where we're getting the anion sublattice to go this direction under field and the cation sublattice to go that direction under field. And then again, when we release the field, when we let go, the bonds holding them together are going to act just like springs and bring those back to their happy point where they're balanced out. And because of that, we see a resonance associated with this as well. And so this schematic here, this cartoon, shows it just for one single cation and one single anion. But of course, this is going to be happening for every couple, every pair, every group of cations and anions within an entire lattice. So you can expand this if you've got a complex chemistry of your material. So for magnesium oxide, just magnesium, just oxygen, you can represent this pretty easily as just the single magnesium cations and single oxygen anions stretching and wiggling back and forth. But let's say you get to a much more complex relaxer ferroelectric that has 9 different cations in it. Each one of these bond pairs and octahedral coordination and every single set of cations and anions within that is going to have its own resonance frequency. And so instead of having just one single resonance peak, you'll see a broad distribution of these for more complex materials. And we'll get to that later on in a bit more detail. But the fundamental individual component still comes down to it's just a spring. And so we can represent that as the higher the mass that's involved, the lower the frequency where we expect that natural spring constant to resonate. And so for example, with barium titanate, you would expect the barium to oxygen bonds to have a lower resonance frequency than the titanium to oxygen bonds because barium is heavier. These kinds of concepts. And we'll see this again as we go. The fun part about these is that these directly relate to the phonon modes that we can measure with things like Raman spectroscopy and IR spectroscopy and similar sorts of measurements along those lines. So we can measure this contribution with index of refraction. We can measure these contributions by various techniques that look at phonon modes and basically lattice wiggling within the material. And so that gives us a little bit of insight into what's happening. You'll notice again, because of that resonance, the peak and loss, there's a loss peak that happens right at that resonance. So it may look attractive that if you want to increase permittivity, that you want to be right at one of these resonance peaks, but keep in mind that there's a broad distribution of these, and if you're at the very peak of one of them, then you're going to be at the minimum part for another one, and this in-between part is where the loss is maximum. And so if you want to dissipate energy, hanging out at one of these resonances is great. If you want to actually store it, it's a dangerous balance to try to match. The other piece that is shown on the slide here, but I forgot to mention explicitly, is that these are essentially additive. So you can just add up the electronic plus the ionic and keep going. And so they really don't interfere with each other too much. What matters for each of these is the local electric field. So to the extent that stretching the electronic contributions, so stretching the electron cloud is going to affect the regional local electric field on the ions around it. Yeah, there's a little bit of interplay there, but for the most part, they're so different in terms of magnitude that you can really just consider them additive. So you can have the index of refraction contribution plus the ionic contribution, and then we can start adding on top of those other polarization mechanisms as we go. All right, so the next one in lower frequency, and unfortunately this plot, when I drew it many years ago, I wasn't smart enough to actually plot it out to scale. So you notice that the frequencies, there's a large gap between each of these. But these sorts of frequencies are generally in the very high gigahertz to terahertz sorts of ranges. At lower frequencies, then we can start getting contributions from permanent dipole reorientation is one example, and that's what I'm schematically trying to represent here by the arrows. So a permanent dipole, the easiest example is just water. So you've got, actually, let's actually draw these as hydrogens. Wow. Apologies again for my poor artwork. But if you've got oxygen with the two hydrogens on it, just naturally, there's going to be a negative side and a positive side to that molecule. And so when you apply an electric field, you can get the molecule to actually flip around and reorient the direction of its spontaneous dipole. So we're really not going to use water itself as a capacitor too often, but the same concept applies when we have a material like barium titanate or like many of the lead-based materials that have a spontaneous polarization. So there's a built-in inside the unit cell has a permanent dipole. We apply an electric field, we can actually get those dipoles to reorient and align with the direction of the electric field. And so the way that I've tried to represent that here schematically is with the alignment of these arrows. You'll notice that they don't all line up perfectly with the field. So I've applied a positive field or positive end and a negative end. The arrows don't line up perfectly relative to where they started. The reason for that is you are crystallographically constrained. So think of water again. If we have liquid water, those molecules can rotate all over the place wherever they want to go. But you freeze that water into an ice cube, and now it's a crystal. Now you apply an electric field. Sure, you can get, you might be able to get the molecules to line up a little bit, but they're stuck inside of a crystal, and so they can't just arbitrarily change their direction. So water is probably a bad example for that because it's not exactly ferroelectric. But if you have a material like barium titanate, where you've got the spontaneous dipole that you can reorient under field, you can change the direction of that orientation to a certain extent, but you can't rotate the actual crystallographic grain. So so you're limited to certain crystallographic directions that you can get that to reorient. And so there are exceptions to that. Well, I guess exception is a strong word. There are examples where we can sort of tweak what those boundary conditions are. So we'll talk a little bit more about relaxer ferroelectrics, where you've got polar nanodomains, where you do actually have flexibility to rotate polarization within unit cells, but that takes a really squishy lattice and sitting right at at a phase boundary where things are flexible enough that you can move around. But we'll get into the mechanisms of this dipolar orientation a lot more as we go. One key about this one, though, you'll notice it does not have a resonance. So as we increase frequency, we don't see a resonance for this kind of behavior. And that's because there's no restoring force. There's no spring that when we align the dipole in this direction and then we remove the field, yeah, it's fine. It was perfectly happy. It was a permanent dipole, so it didn't really care if it was this direction or that direction or this direction. So what is it that's going to lead to reorientation of those dipoles after we get rid of the electric field that's forcing them to be lined in some way? It's really just thermal energy. So disorder associated with thermal energy is going to cause those dipoles to relax and eventually go back to being random. And so this behavior is represented as a relaxation rather than a resonance. All right, any questions on that? Yeah, don't be afraid to jump in if you have questions along the way. You'll notice with the relatively sketchy numbers that are thrown on the vertical axis here, the relative permittivity, as I mentioned, associated with electronic contribution, with index of refraction, you might get a relative permittivity of 2 or 4 or even 5, something like that, just from the electrons. That's pretty small. From the ions, there are a handful of materials where you can actually get ionic polarizability, ionic relative permittivities as much as 30 or 40. But that's still relatively small compared to the values that you can get for these other polarization mechanisms. So if you want something that has a very high permittivity, and if we go back to the capacitor model, high permittivity means high amount of charge that we can store, and high amount of energy that we can store, then you're going to have to take advantage of some of these other polarization mechanisms. So dipolar orientation is one of them. And then we get to even lower frequencies. And then we've got things like mobile carriers or Faradaic reactions like you have in a battery. There are a lot of different mechanisms that you can that can contribute to relative permittivity down here. So the cartoon that I used to describe that is you've got ball bearings inside of a can, and you tilt it one way and they all rush down until they hit the edge of the can, and then you flip them the other direction and they all run down and hit the other edge. It's the same kind of thing. If you have mobile carriers, and that could be ions, it could be electrons or holes or whatever, if they're easy to move within the material, you apply an electric field, they're going to respond. You're going to pull the electrons, the mobile electrons, over towards the positive end of the material. And then you apply a field in the other direction, and they're going to go running back the other direction to the to what is now the positive field. In order to actually store any of that charge, though, you need them to pile up somewhere. So if all the charges are just moving under an electric field, that's a conductor. If you want it to actually be an effective capacitor, then you need the charges to go a certain amount and then stop. And so there have to be barriers in there somewhere that are going to stop those charges from moving, and you can build up a large amount of charge stored. So there are a whole class of capacitors that are built on this idea of having conductive grains and insulating grain boundaries. So you've got a lot of free carriers within the grain that you apply a field and they all fly over and run into the grain boundary and hang out there. And then you apply a field in the other direction and they all run over and pile up the next grain boundary and hang out there. Those are great for storing a very large amount of charge at low voltages. But because those grain boundaries are very thin, and if you remember the mixing rules that we talked about, when you have a low permittivity material, you're going to drop a lot of field across it. So if you end up applying too large of a field, it's easy to get breakdown in those kinds of capacitors. And so they're great for low voltage. They get more and more challenging as you try to increase the electric field or the voltage that go in them. Another aspect would be for batteries. So if you've got some sort of an actual chemical reaction that's happening, you're moving ions, and then there's a reaction that happens, and that reaction allows you to keep the charge carrier right there where it is. and then you apply the voltage in the other direction and drive the reaction the opposite direction and move those charges across the electrolyte to the other side. That's essentially what happens in a battery. And you can store massive amounts of energy compared to traditional capacitors in batteries. The problem is the energy associated with those reactions and the time associated with those reactions means that these are happening at very low frequencies compared to the rest of the plot here. And so depending on all of the factors associated with that, so the kinetics of what's moving, whether or not there are reactions happening, these kinds of contributions are happening at very, very low frequencies. So it might be millihertz, it might be hertz. You're going to be very lucky if you can find a battery that can respond faster than 1 second for large amounts of charge. And so it's the kinetics of those reactions and then all of the other challenges associated with that. So the fact that you're doing chemical reactions, there's strain involved and there's other chemical barriers. So we're not going to talk a heck of a lot about batteries and electrochemical cells in this class unless I get requests to throw those in at the end. So from a capacitor perspective, we're going to focus mostly on these three, and every now and then we'll talk about how having mobile carriers present can lead to very large capacitances, but also often very large losses that are going along with those mobile carriers moving around and bumping into things. All right. Any questions on polarization mechanisms? So these are, again, relatively additive. We can just take one contribution and add it to the other ones and add it to the other ones and build up the overall relative permittivity that we're looking for. But again, each one of these comes with its own caveats and challenges along the way. This is a plot that I stole from the literature, as referenced here. And it's a little low resolution, and so I apologize for that aspect. But one aspect that I did like about it is that it has these frequency ranges listed down here in areas that you're probably more familiar with. So the electronic polarizability, the index of refraction parts, these are happening up in the visible. The atomic polarization, this is microwave to infrared, and then dipole polarization. Where these relaxations happen depend entirely on the dipoles themselves and the matrix within which they're rotating around. So it might be in the microwave, it might be in the UHF. In some cases, you might be able to push these up a little bit higher in frequency, but there's very large ranges associated with each of these. But I like the fact that this laid it out with audio and radio and other aspects that you may be more familiar with. All right. Now for those resonances. So I mentioned that it's just a simple harmonic resonance that we use to describe these basically masses on a spring. It's the exact same equations. You may have seen this one in a physics class at some point. It really is the exact same thing. It's just you look at each one of these pairs of ions as a spring, and then you just add them all together, and you can describe the resonant behavior. So the increase as you're getting close to the natural resonant frequency, and then the dissipation as you get above it. And as I noted briefly on the earlier slide, the peak in this loss happens right at that natural resonant frequency, right at the omega naught, right in the middle of this. And on this one, when this one in particular is talking about the infinite relative permittivity, so that's just a nomenclature for the optical aspect of it. So because it's related to the index of refraction, the index of refraction is like relative permittivity defined relative to free space, and so if you can't go below the relative permittivity, the index of refraction of a vacuum, unless you happen to be at a resonance. So that's why they wrote it here as -1 with a 0, because relative permittivity or index of refraction of 1 means that you're exactly the same as free space, and anytime there's any mass around, it's going to be greater than that. unless you happen to be at one of these frequencies. So a fun side section of science and engineering of the last 20 years is people are recognizing how to artificially build and measure and engineer with materials that take advantage of these weird resonance behaviors. And so it gives you a whole class of metamaterials that can give you a response that a single individual monolithic material can't. So you can actually operate with negative indices of refraction and fun things like that. So if people are interested in metamaterials, we can get into that as well. But that's a fun side topic. All right, so that's resonances. These are the springs. I like to think about this, and we'll come back to this a lot more when we start talking about piezoelectrics, but I'm more familiar with the model of a mass on a spring, and as you sit there and it vibrates. That's this model where you've got a spring, a mass, and then a dashpot, which is slowing things down or dissipating energy along the way. There's the electrical analog to that is exactly the capacitor is storing energy. The inductor is the mass that's driving that. And so you can get a resonance between the mass and the capacitor. And then you've got a resistor that's going to dissipate that energy. And so you can have a resonance frequency in a circuit exactly the same as you can have a resonance frequency in a ball on a spring sort of model. And the equations work out to be the same sort of thing. So fun aspect of that from the capacitor and inductor components. So a capacitor stores the energy in an electric field. So that is the energy storage mechanism for a capacitor. You've got an electric field across an insulator, and that you have the charges on either plate, but it's the field within the insulator that's actually storing the field. In an inductor, you're actually storing that same energy in the magnetic field. So you have current flowing, and anytime you have current flowing, Maxwell's equations tell you that you have to have a magnetic field associated with that. And so if you have just a capacitor and an inductor with no resistor around, you can have a circuit that just sits there and oscillates back and forth and back and forth and back and forth with no dissipation, just the exact same as a mass on a spring with gravity, oscillating back and forth with no, if there were no friction, no dashpot or no dissipation there, then it would just keep oscillating forever. So same sort of concept. Hopefully that helps visualize what's actually happening in some of these a bit better. All right, so that's for the resonance mechanisms. For the relaxations, I mentioned that the reason that those permanent dipoles, or maybe the electrons that are behaving like ball bearings inside of a can, the reason that they end up dissipating, it's not because there's a restoring force. There's no spring. They're just relaxing because thermal energy tends towards disorder. So the more thermal energy that's around, the faster this is going to happen. So these relaxations will have a very strong temperature dependence, because the more thermal energy, the more drive to disorder, the faster things are going to relax. So you can, if you heat something up, you'll be able to align the dipoles faster. You take that field away and they're going to relax faster. And so that's the temperature dependence of these kinds of things. But the equations that are used to describe the relaxations, this is Debye. So Debye wrote down all of these equations, and we still use them to represent what's happening in a relaxation. So again, we're not going to do any homework questions on these equations or anything, but they are really helpful references to have in case you do end up needing to quantify any of this behavior in some way. One thing I should have pointed out earlier, you'll notice on here, there's the epsilon r prime and double prime. And so the prime is really just the real portion, and the double prime is the imaginary portion. So if we go back to the earlier discussion about the real and imaginary components of capacitance, then this is just another way of representing those. So a very important side note. So the complex relative permittivity. Relative permittivity is a complex value. So if you remember back to physics, you can't represent you can't earnestly or honestly represent a complex value with just one of its components. So you have to have both the real and the imaginary portions in some way. So it might be the real part of the permittivity and a dielectric loss that where you've convoluted these, or it might be tan delta, where tan delta is just the ratio of the imaginary portion to the real portion. There are many different ways of representing these, but keep in mind that because permittivity is a complex value, a complex entity, if you only show one component of it, that's basically useless because you're not telling the whole story. So if you ever read a paper or see on a spec sheet someone that is reporting the relative permittivity, the dielectric constant, and they just give you a single number, and it doesn't have anything about loss, it doesn't show any representation of tan delta or loss or dissipation or anything like that, then it's basically useless because they're not telling you the whole story. So it is a complex value that has to have both components somehow. And if somebody reports just one of them, they're hiding something from you. So keep that in mind. All right. So now that we have way too much math associated with the different individual components, we can start to put these together and use them in some way to understand what's happening within our material. And so there's a huge field of impedance analysis, and I'm only going to scratch the surface here. If people are interested in going into more detail, I'm happy to do that, but I also didn't want to bore people to tears with a lot more math. The point is, if you are trying to understand what's happening within your sample, and you don't have the world's most amazing microscope that doesn't exist, where you can zoom in and look at the atoms actually responding and watch where the electrons are going, then the best way to understand what's happening, one of the best ways to understand what's happening, is to do impedance analysis. So you apply an electric field and you change the frequency and the magnitude of that field. So you apply a small electric field and then you go faster and faster and faster and faster, or slower, however you want to do it. And that can start to tell you the frequency dependence of whatever you're measuring. You can also do this as a function of temperature, as a function of the magnitude of the field, these kinds of things. What I'm showing you here just as a first step is you're just changing the frequency. And by seeing the way that the material responds differently at different frequencies, we can start to back out which polarization mechanisms are contributing in different ways. So you can plot this either as the change in the imaginary portion of the permittivity as a function of frequency, and that shows you, oh, there's some sort of lossy mechanism that's maximized right at this frequency. So maybe that's where there's a relaxation. Maybe there's a resonance right there, where there's a something that's happening that I'm maximizing the loss. I'm dissipating a lot of energy there because of one of those polarization mechanisms is relaxing out. When you plot these over the real part of the impedance versus the imaginary portion, you can end up with these semicircles. And each one of those semicircles will represent a different polarization mechanism, a different relaxation that's occurring. And so often these will be reasonably independent from one another. Sometimes they'll start to overlap, and modeling, so the orange lines on here are meant to represent the actual data that are measured. And then the semicircles are what you've built up a circuit and said, if this thing that is happening is, here's a capacitor and I have a resistor in parallel with it, and here are the values of each of them, it's going to give me this kind of a semicircle. And then I have another polarization mechanism that's a separate portion of the sample. Maybe this one represents the grains and the other one represents the grain boundaries. Then I can start to say, if this is if this circuit model represents my sample and it matches up with the data that I've measured, then I'm going to interpret that as the grains as a whole have this capacitance and this resistance, and the grain boundaries as a whole have this capacitance and this resistance. And so that's the super hand-wavy approach to impedance analysis, but that's basically the way that we have gradually built up an understanding of what's happening in these complex microstructures. You can do the same sort of plot as a function of frequency, and you can see that as you increase frequency, the impedance is dropping here. And that's because there's one of your polarization mechanisms just can't keep up. So that might be the mobility of your charge carriers. If you have conducting electrons is low enough that they can't respond really fast, or maybe you're at the point where you're stretching the ions between lead and oxygen, and you're wiggling fast enough that the high mass lead just can't keep up. And as you do that, the phase angle will change, as we see over in the plot on the right. So the phase angle is going to be that the angle that we were talking about representing with delta. And the two different colors here are meant to represent two samples or two different temperatures or something along these lines. And so this is a suite of tools to help understand what's actually happening in the materials. But in order to make sense out of these, we have to understand the individual components like we just went through, where you've got the capacitor in series with a resistor. Over here, you've got a capacitor in parallel, and you end up building up large models. And I say model, but it's really just a circuit model made up of these very simple components. And you say, what if this is what it looks like? Then here's the response I'm going to get. And what if this is what my sample really represents? Then I would expect this kind of response. So Alexa, hopefully that addresses your earlier question at least a little bit. We will, when we make these measurements, of course, they're usually on macroscopic samples. So you've probably got millions or billions of individual grains, and you have to treat them as the overall average grain boundary does this. The overall average grain does that. And if you want to zoom in on individual grains or individual grain boundaries or some other mechanism, then you've got to get a little more clever with your direct measurement. But these kinds of techniques, even on bulk samples, can give you a lot of insight into what's actually happening if you have some idea of what might be going on in the sample. So based on all that, I want you to think about how you might be able to apply some of these different concepts to whatever it is you're working on. So maybe you're not making capacitors, but maybe the samples that you're creating, you want them to be transparent to a certain frequency, and so you don't want any electrons and the mobile electrons to interact with photons at a certain frequency or something along those lines. So just think about how you might be able to apply, or maybe it's a scenario where you don't actually care about the electrical properties of your final product at all, but you want to use these electrical properties as a probe of what's happening. So as we'll get into in the next section, there's a direct relationship between electrical conductivity and point defects. And so maybe you care about the point defects for a diffusion and sintering concern. You don't really care about the electrical properties, but the electrical properties let you measure defect concentration in some way. So think through that. Again, you don't have to email this to me at all, but I do want you to think about it because I want you to find a way that this can be directly applied to what you're working on. All right, so we'll have just enough time to introduce point defects, and then they'll give you something to have nightmares about over the next few days before we come back and talk about them in more detail. So I use the examples here are ruby and a blue sapphire, because the only difference between them are the presence of parts per million defects. So sapphire, ruby, they are both aluminum oxide. Ruby, the red one on top, has some extra chromium defects that are hanging out in place of the aluminum. And sapphire has titanium and iron defects, and the charge interactions with photons is what ends up giving you the red color for chromium or for ruby, or the blue color for iron and titanium. And these are just very visible examples of the impact of point defects, which is what we're going to be talking about next. All right, so in order to actually describe point defects, we use Kroger-Vink notation. And so the first thing that you have to remember for any of this is that we are starting from a point of assuming the absolute perfect lattice, no defects. This lattice goes on forever. And so we are going to describe everything as a deviation from that perfection. So we don't describe the whole lattice. We just describe what's different about our actual sample from what that perfect defect-free lattice would be. And so because of that, we represent the charge of a defect as the relative charge compared to what it would be if that defect weren't around. So in this case, we're talking about an oxygen vacancy. So the V is vacancy. Oxygen is a subscript down here. And then the charge is, we're going to use circles or dots for a relative plus charge. And that's because oxygen itself, the oxygen ion, is -2. The absence of an oxygen, so the lattice is expecting an oxygen to be there. If that oxygen were there, that would be our baseline 0. But because there's not an oxygen there, the vacancy is +2 charge because we're missing the negative that we would have otherwise. Hopefully that makes sense. The other kinds of sites that we can have besides just sitting on a particular chemistry is we can have an interstitial. So it'll be a lowercase I for interstitial. So that's shoved into the open space where there's no atom. And then every now and then we'll throw surface on there just to explicitly represent a sample hanging out on the surface of a sample, or an atom hanging out on the surface of the sample. All right, so hopefully covariant notation makes sense. You can use this as a reference, come back to it. We'll start off with the stoichiometric defects. So these are the ones that are so prevalent, they're everywhere. They get their own fancy names. So Schottky and Frenkel were the people that discovered these, or at least first described them. And therefore the defects are named after them. So Schottky defects are stoichiometric vacancies. So that means whatever perfect lattice you have, it has some sort of stoichiometry to it. So if it's magnesium oxide, that stoichiometry is 1 magnesium and 1 oxygen. So a Schottky defect is going to be, I lost one of each. And so the easiest way to think about that is they got shot out of the lattice. And so you've got a stoichiometric set of vacancies. So it's not just a vacancy pair. In this case, it happens to be a pair, but it has to be stoichiometric for whatever that lattice is. A Frenkel is where you started off with, there used to be an atom here, and it hopped over into an interstitial site where there shouldn't be anything. And so Frenkels always do come in pairs because they are an atom that moved out of its home where it should be in the perfect lattice and moved into an interstitial site somewhere else where the perfect lattice would have nothing. So those are the baseline stoichiometric defects, Schottky and Frenkel. We're going to see them over and over again, but we're also going to get into a lot more options. So we're going to write reactions for these because these are chemical reactions. So you can start with a baseline lattice and say, what happens when I start with a perfect lattice and then end up with a Schottky defect, or I start with a perfect lattice and then end up with a Frenkel. And so these are chemical reactions. We have to conserve mass, we have to conserve charge, and we have to conserve structure. And the first one is pretty easy. You just count up atoms. The second one is pretty easy. You just count up charges. The last one, you have to remember that we're talking about a deviation from the perfect lattice, whatever that lattice is. So if we're doing a chemical reaction, talking about defects within magnesium oxide, then I need to have 1 magnesium site for every oxygen site that I'm dealing with. And so those sites might be filled, they might have a different atom in there, there might be a vacancy. But for every, I have to have a stoichiometric number of them. So I have to keep 1 magnesium per 1 oxygen. If it's for alumina, I need 2 aluminum sites for every 3 oxygen sites. So I just have to keep consistency with whatever the baseline lattice is. And so I can actually increase or decrease the number of those basically unit cells. So I can add an extra Al2O3 on top of the surface because this whole approach is describing everything relative to an infinite lattice. So infinity plus one is still just infinity. Infinity minus one, still just infinity. So I can add or remove stoichiometric numbers of those sites as long as I do it according to whatever the chemistry of the baseline crystal is. So if I want to write a reaction for Schottky defects, these are the ones that are shot out. So the easiest way to do this, I'm going to just use magnesium oxide because it's nice and easy and matches the stoichiometry of the figure that I stole from Carter Norton's book. So we're going to start off nil or sometimes null. People will write either of those, and in these slides I have examples of each of them. They're completely identical. That just means I'm starting from the baseline, and that baseline is the perfect lattice with no defects, no boundaries or anything like that. This portion just says, yep, it's a chemical reaction. I can technically go in either direction. I like, just for bookkeeping purposes, to throw the above that reaction arrow, remind myself what the material is that I'm talking about. So that technically doesn't have to be there, but it reminds me what my baseline is. So this is happening in magnesium oxide. That means I need to keep one magnesium vacancy or one magnesium site for every oxygen site and vice versa. Because this is a Schottky defect that I'm talking about, I know I'm going to end up with a stoichiometric set of vacancies. So that defines a Schottky defect. So all it means is that I've got magnesium vacancy, an oxygen vacancy, and they came from the perfect lattice. That equation represents the Schottky defect. Any questions on that? All right, I can do the same thing. I mentioned before that I could just add surface sites. So if I've got a magnesium oxide lattice, I start with magnesium and oxygen. Those atoms that were shot out of the lattice as Schottky defects, maybe they just went up here and landed on the surface. That's completely equivalent to what I just wrote for the nil going to a vacancy pair. Yes, Alexa, sorry for the confusion there. The open circles equal the closed circles. It's really just a circle versus a prime for positive versus negative. And that's, instead of just using pluses and minuses, we use the circles and the primes as a reminder that these are relative to what the site should be. So it's not actually, so the oxygen vacancy is not actually +2 charge. It is relative to having the oxygen there, it would be +2. So that's why the nomenclature is a little funky. So we can write the Schottky defects either as just nil going to this vacancy pair, or if we want to keep track of everything, we can say that we started off with magnesium and an oxygen sitting on their sites, and then they went to a vacancy and another vacancy, and those atoms ended up on the surface. And that's what's represented in the figure on the right. But for simplicity, we can just go through and say, well, those cancel out. And we end up with the little bit simpler equation. But just remember that that's what we're talking about. We're not eliminating mass. We're just shifting things around. So hopefully that's not too terribly confusing. We're going to get more complicated as we go because that's what we do. All right, so these are for Schottky defects. The other, these are completely equivalent. So it doesn't really matter which one of these you want to use. Just be sure that you are maintaining charge, mass, and stoichiometry and sites. All right, so if we were to do the same thing for a Frenkel, so this is a case where we had an atom here and it hopped over into an interstitial site. What would that look like? Let's do it for lithium fluoride, another simple 1-to-1 rock salt sort of material. And in this case, I used null instead of nil, completely equivalent. So we've got a lithium vacancy and a lithium interstitial. So you'll notice I didn't bother to put the fluorine on there because the fluorine sites really aren't engaged in this reaction in any way. They're still there. They're just encapsulated in the neutral perfect background. And so if I really wanted to do that, if I wanted to do the Frenkel defect as rigorously as I did for Schottky, I would need to write out the entire equation that said lithium over here, fluorine over there. The fluorine is sitting on a fluorine site, so that would be fluorine on a fluorine site with no charge, and extend that out. But they can end up canceling out when you get done. So what would it look like for alumina? In this case, we're going to have alumina with the reaction arrow. And so for a Frenkel defect, by definition, a Frenkel defect means that I have an ion in an interstitial site. And in this case, that's 3+ for an aluminum interstitial. Anybody want to take a crack at what this would look like to fill out the rest of the equation? Probably going to need 2 of them so that I can have a stoichiometry involved. And then because it's a Frenkel, I know that for every interstitial, I also have a vacancy. And so I have 2 aluminum vacancies, and each one of those is -3. And then I can add in the 3 oxygens on oxygen sites. And over here, I have 2 aluminums on aluminum sites, plus 3 oxygens on oxygen sites. Hopefully that matches. Or you can do it with the half. So life gets easier with if you want to use fractions. All right, hopefully that makes sense conceptually. So now we can move on to even more fun aspects of this. So because these are reactions, we can write equilibrium constants, just like we did in whatever early chemistry course you took. So it's you've got a reaction, so you've got some sort of distribution of equilibrium that you can describe for that. So it's just products and reactants. So for example, using the MgO Schottky, write it out as a vacancy, a magnesium vacancy plus an oxygen vacancy. The equilibrium reaction constant for that is just this K is just described by the product of the products. So you multiply the concentrations of the products together, and if there were a reactant, then you would write that underneath here. In this case, it's null, and so we can just ignore it. So that's the equilibrium reaction constant for this Schottky equation. And it just tells us that the equilibrium is going to depend upon the concentrations of these different species. You do the exact same thing for the lithium fluoride example. And again, you've got the concentrations. So the brackets here refer to concentration. And a very important aspect of this is in the box here. So the assumptions for all of this, just like in any basic chemistry, for these to apply, so to be able to go from the concentrations of these products is what leads to the rate constant. The assumption is that these are dilute, non-interacting species. If they do interact with each other, then you can't make that leap to the rate constant is directly related to the concentration because there's going to be other factors involved. But this is a good place to start. And even when we know that the defects themselves are interacting, so you might have yttrium stabilized zirconia with a very high concentration of oxygen vacancies, we can still use these equations as a good starting point. And then we make minor tweaks away from them to say, all right, so these oxygens are interacting with each other this little amount, we're going to shift the result that we get by this tiny amount to a correction factor. But these are a good place to start. Just remember that the baseline assumption is that they are non-interacting. So the other piece of information that we have is that we know that everything has to remain electrically neutral. So if this is at equilibrium, we can't just magically build up positive or negative charges. So because we know it's at equilibrium, and all of this is going to assume equilibrium, that's what this arrow is telling us, that it can go in either direction. Then because it's at equilibrium, we know that all of the positive charges have to sum up and equal all of the negative charges that are happening in this reaction. So that means that because magnesium and oxygen have the same relative charge in this case, the concentration of oxygen vacancies has to equal the concentration of magnesium vacancies. Same with the lithium situation. This is going to get more complicated as we go. But just remember that because these are chemical reactions, we can write equilibrium rate constants. And because we're assuming that it's equilibrium, all of the charges have to end up balancing. And so I will give you just a teaser of where we're going to go next. I guess we'll get one more equation that we can deal with. We talked about electron hole pairs when we were talking about conductivity. So technically, this creation of an electron in the conduction band and a hole in the valence band, you can represent in the exact same kind of manner. So a photon comes in. This is what happens in a solar cell. Photon of light comes in and excites an electron from the valence band to the conduction band. We can write that out just like this, and we can simplify it to say we got an electron in the conduction band, we got a hole in the valence band, and then the equilibrium rate constant is the product of those two. And then at equilibrium for electron neutrality, if this is the only thing happening, then they have to equal one another. And by convention, the way that we write that, the concentration of electrons is just N, and the concentration of holes is just P. And so we will use these again as we go. I'll give you just a quick teaser of where we're going with this. Is now we're going to start dealing with non-stoichiometric point defects. So now we can start putting in donor dopants and changing the oxygen concentration in our material, or intentionally introducing electrons and changing the concentration of other species, that we can change kinetics for diffusion and these kinds of things. So we'll get to that next week. If anybody has any questions along the way, please shoot me an email, and I'll do my best to either answer directly or answer to the whole class when we come back next week. Any questions as we wrap up here?
So if we were to apply a field to the Schottky or Frankel defects, would an interstitial or a vacancy have a higher mobility?
That great question, and that depends entirely on what the material is. So, for example, if it's a lithium interstitial, it's probably going to be pretty easy to move because lithium is only +1. It's not a huge ion. It's something that's how battery electrolytes work, because you can move lithium ions around. If it's a vacancy, maybe if it's an oxygen vacancy, in most of the materials, most of the ceramics we care about, the oxygen sublattice is close packed. So it's easier for oxygen vacancies to hop from site to site to site. But each one of those is going to have their own temperature dependence. And you're going to have different kinds of other barriers that might get in the way. So maybe you run into a grain boundary, and that particular grain boundary is such that it's really hard for the oxygen vacancy to get through. Or maybe it's a superhighway for the lithium to conduct. And so there's no one easy answer for that, but you're thinking along the right lines, is that, yeah, the mobility is going to be different. And how is it different? Well, then we'll have to go do some measurements on that particular sample to figure it out. All right, if there are no other questions, thanks everybody for tuning in. I will see you next week.
Thank you.